And so today we're gonna be solving or explaining chapter 4 for chemistry. So chapter 4 is all about oxidation and reduction reactions, and it starts off with telling us what's combustion. Combustion is when you react, like as you can see, it's telling us when you react a gas and you produce large amounts of heat and light, and they're usually reactions with oxygen. This is an example of a redox reaction. Now, not all the reactions will produce light, and that's another thing you should keep in mind. For these, most of them, you have to read the document and understand it. And yeah, I have a little thing to add about these 2 points here. Oxidation, how to remember if oxidation is loss of electrons or of its gain. Remember the 2 words, oil and rig. This stands for oxidation is loss, reduction is gain of electrons, of course. Remember, whenever you have electrons, memorize these 2 words, and they'll help you in remembering. Now, I'm going to start with the CQDs. Now, first of all, we need to know this paragraph if you want to solve anything with oxidation numbers, but I have it in a table which I'm going to write down. I find it easier to memorize a table than the paragraph. So let me get the table and I'll write it down. Okay, so to assign oxidation numbers, let me make the font smaller. And we have a table. Here are your species and their oxidation numbers, examples/exceptions. So our first thing is if you have an element. Our elements, whenever you see an element by itself, its oxidation number is always without exceptions, always 0. The elements always have an oxidation number of 0. Some examples are sodium, Na, I2, doesn't matter the subscript, by the way. Even if you have a subscript, you don't look at it. If it's just one element or one capital letter, it has an oxidation number of 0. I2, O2, S8, all of them, oxidation number 0. For 2 are your simple ions. For the simple ions, your oxidation number depends on the charge of that ion. I'm gonna tell you what I mean by charge now. Let's say Na plus, the oxidation number for this would be +1 because it's plus. Or O2 minus, its oxidation number would be -2 because it's 2 minus. Or one more example, Mn2 plus. It would have an oxidation number of +2. These are for simple ions. Now here's the more confusing one, compounds. For compounds, it depends. If you have fluorine, your oxidation number is -1. If you have any group 1 element, it's +1. If you have group 2 element, it's +2. If you have aluminium that's in group 3, it's gonna be +3. I think you get the idea. Group 4, you can't identify its charge. Group 4, always you have to calculate it or find it. But yeah, halides, if you have a halide, it's -1, except with fluorine. So except, here's our first exception. except with F or O, then you have to calculate it. And then you have two more oxidation numbers, oxygen I mean. Oxygen has an oxidation number of -2, except with fluorine again. Then it would have, except with fluorine, it would have an oxidation number of +2. +2. And with peroxides, it would, like for example H2O2, it would have an oxidation number to -1. Now last one is hydrogen. Hydrogen, it has a oxidation number of +1, except with metal hydrides, or with the metals in the metal hydrides. Metals in metal hydrides. So these are all the rules you have to remember for your oxidation number. And of course, the sum of the oxidation numbers must equal the charge. Also remember this. So that's how you assign the oxidation numbers. Now let's start solving and finding oxidation numbers for these species. Now I'm gonna have the answers here, but I'm gonna explain how you get each one. Let me make the pen bigger again. Sorry. So for A, NH3. So in our table, we said hydrogen is +1. So the ones you know, which in this case is hydrogen, you put it directly. So hydrogen, it's always +1 unless with the exception. So you just immediately write down +1, and now you need to find the ones you don't know, which in this case is nitrogen. So since hydrogen is +1, you need to find it by doing +1 times the subscript. So now you have +3. You write whatever you don't know as x equals whatever the charge of your compound is. Here your compound doesn't have a charge, so it's 0. So x + 3 equals 0, x equals -3. So we know that n would be -3. And -3, hydrogen +1. And that's how you find it. And don't put the charge for hydrogen +3 since it has a subscript of 3. The oxidation numbers for the known ones, or for all of them, don't rely on the subscript. It matters on what you know the nature of that compound, that element's oxidation number is. Now that's for part A. Now part B. For part B, you have H2CO3. Now we know that H, like we said, is +1, and we know that O is -2. Now we don't know C. C is our x here. So +1 times the subscript, which is 2, gives you +2, plus x plus -6, because -2 times 3 is -6. Here you could remove the plus and just write upright -6 equals the charge of the compound, which is 0. So plus 2 or 2 plus x minus 6 equals 0. So it means x minus 4 equals 0. X equals 4. So C would be equal to plus 4. And that's how you find for this one. C, H is plus 1, O is minus 2, C is 4. Now for C, I won't explain it because C is just immediately 0 because this is a element. It's not a compound. So you don't have to find it. Now for part D, you have MnO4 minus. Here we have to do something a little different because there's a minus. So we know O, negative 2. And Mn, we don't know it, so X. X minus negative 2 times 4 is minus 8 equals, this time it's not 0. This time your compound has a charge, which is minus. If it says minus, it means minus 1. So equals minus 1. Then you move the minus 8 to the other side, making this negative 1 plus 8, which is 7. So Mn has an oxidation number of 7. And that's how you solve part D. Now we have to solve for part E. So E is Cr2O7 2 minus. Here we're gonna do something. This one's different than the other explanations because Cr here has a subscript and we don't know it. O, like we said, always negative 2 in this case. And since it's negative 2 and this is X, but be careful. If the thing you do not know has a subscript, you have to multiply X by that subscript. So here it's 2X minus negative 2 times 7 is negative 14 equals 2 minus means minus 2. So 2X equals positive 12, making X equal 6. So Cr's oxidation number would be 6. And that's how you solve for oxidation numbers in this CQD. This is CQD 10. Now here, they're telling us a few things. When we add, like oxidation is always when you increase the oxidation number, and reduction is when you decrease it. And if you want to know if a reaction is redox or not, it would be redox if you gain and lose atoms of oxygen and lose or gain electrons. And we need to memorize these. When you want to know if a certain solution underwent redox or reduction or oxidation, if it's potassium manganate, it will turn from purple to colorless. But if it's potassium iodide, it will go from colorless to brown. And that's our next CQD. When acidified potassium manganate is added to a reducing agent, the color changes from purple to colorless. And when you add potassium iodide, which is a reducing agent, to an oxidizing agent, it will turn brown in color. Now here they're asking us which of the following are redox reactions. Now I'm gonna delete everything I have written and I'll re-explain it. Why it's a redox reaction. Or which, they're asking us one of these is a redox, they're asking us which one. Now we're gonna know how to find it. Okay, so for the first one, the best way to find any of if it's redox or not is by using oxidation numbers. It's the safest way, or like the one that you can't go wrong with, really. So if you see any change in oxidation number for each element from reactant side to product side, then you have redox. If you don't see a change, then you don't. Or if the number of oxygens, but we'll explain that one later. I find it more confusing. So here we know that, for this one, we have two unknowns. So we can't really use oxidation numbers, but this one, it's really easy to know because of the oxygen. Here you had O3, here you have O1, and here you have O2. So in the reactants and the products, you have the same number of oxygens. Even if there was no change in the number of oxygens, you don't have redox reaction. So this one, not redox. It's not the correct answer. Now the second one, you could use the oxidation numbers here. So Zn, we know O is -2. If this is -2 and their overall charge is 0, then this must be +2. Here, H is, where did it go? Sorry. H is +1. Cl is -1. This is a halide, that's why. Now here, Cl, it's -1. By the way, this 2 is supposed to be a subscript. And since this is -1 multiplied by subscript 2, it will give you -2, then Zn here is +2. H is going to be +1 and O is going to be -2. So here we're going to compare. Does Zn have the same oxidation number here and here? Yes. O will always have the same oxidation number. H has the same oxidation number. And Cl has the same oxidation number. Since there was no change in oxidation numbers, it's safe to say this is not a redox reaction. So we're going to remove this and write not redox. Now for the next one, we know that Cu is an element, so it has an oxidation number of 0. O2, also an element, so oxidation number of 0. CuO, O will have oxidation number of -2, while Cu will have an oxidation number of +2. So since here this was 0 and it changed, and here it was 0 and it changed, this is immediately redox. Now for part D, you also have to do the same thing with the oxidation numbers. Now let's start. So HCl, I'm gonna leave this one till the end, is +1. Cl is -1. NaCl, +1, -1. H, +1. This -2. C, this here is -2 multiplied by 2, -4, so this will be 4. Now here, you have Na, which is +1, O, which is -2, and Na will be +2, so 2 plus x minus 6 equals 0, leaving x to be, when you calculate it, 4, +4. So again, compare all their oxidation numbers for the species. Na did not change, C did not change, O did not change, H did not change, Cl did not change, nothing changed here, so it's not redox. Now, for the next one, it's not a CQD, but I'm gonna explain it, but there's no answer for it, like no answer sheet for it, but my answers are correct because I copied them down in class. Now, they're asking us to identify which ones are redox, and if they are redox, which ones are oxidizing and reducing agents. We skipped it up somewhere. It says that about oxidizing and reducing agents. Yeah. A reducing agent is an agent that reduces something else and is oxidized. So reducing agents are the ones that are oxidized, but they reduce the other one. Oxidizing is the one that's reduced and oxidizes the others. Forget the fact that it oxidizes or reduces the others, just know first if it's getting reduced or oxidized, so you can know if it's which one is it. So here, when you find the numbers, so this is +1, -1, +1, -2, +1, -2, minus, and this here is -1, because the charge is -1. No, it's not an element, by the way, be careful, this is an ion. So here, when you compare all the oxidation numbers, nothing is changing, so this one is not redox, so you don't need to specify which one's oxidizing or reagent, because it's not redox. Now for the next one. Now AgNO3 is aqueous. We need to find the charges. Now NO3, they should put brackets around it, but NO3 is something that we had it last year in our chem book in a table. NO3 always has a charge of -2, if I remember correct. Actually, let me check so I'm not giving wrong information. Okay, so actually it's -1, not -2. I'm sorry about that. I forgot them because there's another one that's -2. But anyways, this is NO3 has a charge of -1. So since NO3 has a charge of -1, we can find the oxidation numbers of each one by itself. -2 here. And since looking at NO3 alone, so if this has an oxidation number of -2, meaning this one, we have to calculate its oxidation number. So NO3 minus, we know that it's NO3 minus, making O3, this one we know it's -2 because it's O. I'm gonna write it, I'm just gonna write it -2 above it. And now we need to find N. So N is our X, and -2 times -3 is -6 equals -1. So N has an oxidation number of +5. Or well, it has an oxidation number of 5, yeah. So this one's -2, and this one's 5. Ag would be then, so X plus 5 minus 2 equals 0. Ag would have oxidation number of 3. So now we know that Cu here is an element, so it has an oxidation number of 0. Here Cu does not have an oxidation number of 0 because it's in a compound. Since we know this is gonna be 5 and this is always -2 from here, when you multiply them by 2, you're gonna get that Cu here has a charge of, so 5, 2, it's X plus 5 minus so it's 5 minus 2, so it's negative, so it's 3 times 2, which is 6. Guys, you know what, for this question, you can calculate the oxidation number of Cu here by doing the calculations we did up, but for this one, it's really simple because look, here Ag used to have any oxidation number since it was in a compound. Here it became 0. So here it had a charge no matter what that charge was, and here it became 0. Here Cu had no charge, and here because it became in a compound, it had a charge. So you could immediately tell that this is number X and this here is 0. Here it had 0 and here it had X oxidation number. So we know that Ag went from being a number to 0. So it was what's it called? It was reduced. Since it had a positive number, which here we found to be 3, it was reduced into 0. So it's the oxidizing agent since it was reduced. Cu went from being 0 to having a charge. So it was oxidized. It went from something small to big, so it was oxidized, making it the reducing agent, as we can see here. That's why, for these questions, I personally don't recommend finding each one's oxidation number. You could just imply that it increased or decreased by making it from 0 or whatever. Now for part C, by the way, these types of questions, they rarely bring them, but I'm solving them in case. So H is +1, C is, since this is +1, C is -4 here. Here O2 is -2. Here CO2, C is, here it's -2, so C is +4. H here is 1, O is -2. Now, oh wait guys, I'm sorry, I made a mistake. O here is an element. I didn't realize, I saw something else beside it. O is an element, so it has a charge of 0. Since O is an element, it went from having a charge of 0 to -2. So it got reduced. It went from 0 to something smaller, so it's reduced, making it the oxidizing agent. Whereas CH4, C specifically, went from being -4 to being +4, so it became bigger, making it the reducing agent. If you didn't realize, the one that's oxidized is the reducing, and the one that's reduced is the oxidizing agent. Imagine they're like opposites always. And here, these three, if I were to do them, it would take a lot of time. You can just solve them, and here's the answers for them. They're the same exact concept as the first three. They don't have any other tricks in them that make them any different. Now I'm gonna go on to the electrolysis. What? I don't know how to speak. Anyways, electrolysis. It's when you decompose an ionic compound when it's molten or in an aqueous solution by passing an electric current. That's the definition. Memorize definitions always. Whatever is in bold, it's a word that you need the definition for it memorized. And we need to know that electrons flow always from the anode to the cathode. These are just some things you need to know. And now we're going to start with the CQD 11. So at CQD 11, it's telling us the electrolysis of the molten lead bromide, PbBr2, is conducted using the apparatus below. You have the positive electrode, aka the anode, and the negative electrode, also known as the cathode. Here it's asking us to write the half reaction that takes place as the cathode. So since it's PbBr2, Pb is the positive ion and Br is the negative ion, or negative. And anode is called the anode because the anions will go towards it, and the cathode is called the cathode because the cations, the positive ones, will go towards it. So at the negative electrode, aka the cathode, the Pb is going to go to it. And we need to know that at the anode, oxidation takes place, and at the cathode, reduction takes place. Well, for the cathode, we have it memorized by the what's it called? The red fat cat. Because at the cathode, the cat, its reduction happens, and the fat is because of another point that's going to come below at the electroplating. It increases in size, but that, forget it for now, it's going to be useful later. So the red fat cat. Cathode undergoes reduction and increases in size. So now we need to write the half reaction that takes place at the cathode, which is with Pb. Since it's reduction, it will be going from Pb, I at the eraser, Pb, 2 plus. If you add to it 2 electrons, this is how you write a half reaction for reduction. The electrons are on the reactant side. And 2 Pb. And that's the half reaction that's going to happen at the cathode. Now at the anode, you're going to have the Br. Br minus, or no, it's oxidation. So it's oxidizing. So Br is going to become Br minus and E the electron, since it's minus 1 electron 1. And then when you want to write the chemical equation, it's PbR2 breaks up into Pb and Br2. That's it, just split it. Now here it's now telling us that you have to use inert electrodes if you don't want them to react with your ions. This is here just an example. You should read it if you want to understand. Likewise here. Now moving on. So the next part is telling us about read these parts to understand them, by the way. It's when you use electrolysis with inert electrodes or with copper electrodes. When you do it with inert electrodes, the electrodes themselves aren't affecting what's the reaction happening, whereas when you use copper, which is something that gets affected by the copper sulfate, it will change the resultant, the products that you get from your electrolysis. So now here are some general rules you need to memorize. That at the cathode, always, you'll either have a metal, or sorry, what did I do? You'll either have a metal or hydrogen is gonna be forming, and the more reactive the metal, the less likely it is to form, and the hydrogen will form instead. For this, you need to memorize these two reactivity chain orders. So if you have H plus and Zn present, it's gonna tell you that the H plus is gonna displace the Zn. It's gonna form in the solution, and at the anode, same thing. If the halides are concentrated, they will be oxidized, forming the halogen. So when it's concentrated, the halogen is gonna form, but if it's dilute or absent, hydroxide ions, which are found in the water, will form oxygen. And this also, it needs to be memorized. Okay, so here's CQD 13. You have concentrated hydrochloric acid, and it's electrolyzed by the apparatus below. Here they want us to label which one's the anode and which one's the cathode. Here, this is the positive side of the battery. So it's gonna connect to the anode, which is the positive side, and the cathode is the negative one, and it connects to the negative side. And when you switch the circuit on, like when you have a closed circuit, the observations you're gonna notice is gases forming because it's hydrochloric acid, which is HCl. And hydrogen is gonna win it's more reactive because you don't have anything else other than water. Hydrogen is gonna form the hydrogen gas. Cl is fighting with the OH, the hydroxide, but as we can see here, Cl will displace the hydroxide because it's less reactive, but yeah. So now you're gonna find gases being produced. You're gonna find hydrogen and chlorine gas produced. So at the positive electrode, which is the anode, what's gonna form? You're gonna have the chlorine gas, because we know that the anode is the positive one that will attract the negative ones. So the Cl is Cl minus. Since it's minus, it's gonna go towards the anode. So at the positive electrode, which is the anode, it will have the minus one. So the Cl is gonna become a gas into chlorine gas. And how do you test for chlorine gas? We know from previous chapter that it bleaches litmus paper. Now here they're asking us which of the following aqueous solutions produce H2 and O2 during electrolysis. Now here we have Ki. K, these are aqueous solutions, so they're all reacting with water, H2O. So Ki is, sorry guys, K is less, it's lower on the scale, it has a least tendency to get reduced than H. So between the K and the H is gonna get reduced and go on to form hydrogen gas, H2 gas. And between the I and the OH, because there's two H's and one O, so it's H plus and OH minus. Between the I and the OH minus, the I has a higher tendency of getting oxidized, so the I is gonna move on to form iodine liquid. It's gonna form iodine. So here you have H2, but you don't have O2 as a result. Now, moving on to the next one. So our second one, CuI2 with H2O, which is H plus and OH minus. Here you have the Cu and the H first, the H plus. We know Cu has a higher tendency. So here, Cu is gonna win and move on to become copper. And between the I2 and the OH, the I is gonna win and move on to be iodine liquid. So here you don't have neither H2 formed hydrogen nor oxygen gas formed. so it did not form the ones they wanted. Now, molten NaOH. Here I think they copied it down wrong. It's supposed to be OH, not Cl. But either way, so because it's molten, it's not aqueous solution, so it won't form this one, so it's immediately wrong. So yeah, here you have CuSO4 plus H2O plus H2O. Cu is gonna beat H plus. It has a higher tendency. It will move on. SO4 and OH. OH has a higher tendency of reacting, so you're gonna have oxygen gas formed, but you're not gonna have hydrogen gas formed. So it doesn't meet all the expectations of the question. Now here, K2SO4 plus H2O. Now from between the K and the H2O, the H plus has a higher tendency to form, so it's gonna form the hydrogen gas, H2 gas. Between the SO4 and the OH has a higher tendency to form, so the OH or the oxygen gas is gonna form. So here you have both hydrogen and oxygen gas, making E the correct answer. Now moving on to the next one. So here they're asking us to fill up the table with the correct products when you use inert electrodes or copper electrodes. When you use copper electrodes, like we said, the copper is gonna affect the reaction of the electrolysis of the CuSO4. So instead of having at the anode the thing you're supposed to have, which is because look, it's CuSO4 plus H2O. So between the Cu and the H, Cu is gonna form the Cu at the cathode, and between the SO4 and the OH is gonna form oxygen at the anode if you were using inert or graphite electrodes, because graphite and platinum are both inert, so they don't affect. So these are your expected results if you're using inert. But since you're using copper electrodes, it's gonna affect on the result of the oxygen, so you're gonna have both copper at the anode and the electrode. Now, moving on. Using inert electrodes like carbon or platinum is better, because it gives you more accurate results. Here they're asking us which of the following products will form on the electrodes of the cells. So you have a concentrated solution of NaBr. We said if it's concentrated, wait, now I'll pick it, but wait, NaBr plus H2O. Between Na and H2 is gonna win and form at the cathode hydrogen, or well, H2 gas. This is H plus, by the way, we don't look at this as H2. And between Br and O, or OH, because it's a concentrated solution, you're gonna let the halide win. So Br is gonna be more reactive and form bromine. So that's your two results, hydrogen and bromine. If you have AgNO3, between Ag and H plus, Ag is gonna have a higher tendency, so you're gonna have Ag at the cathode. Between NO3 and O, you're gonna have always OH, which is gonna form oxygen or O2 gas at the anode. Now, between this and KBr, you're gonna have between potassium and hydrogen. Hydrogen is gonna go on to be at the cathode, and it's gonna be hydrogen gas, by the way, so H2. And between Br and O, since it's a dilute solution, you don't care that Br has a higher tendency, you're gonna have oxygen forming at the anode. So OH is gonna form oxygen. And that's it for this part. Now our next part is talking about electroplating, which is using electricity to cover things to make their appearance better or to protect them from erosion. And here is where we get to use the red fat cat. Red fat cat. Because the thing you want to plate or cover is you're gonna put it in, instead of the cathode on the negative terminal. So you're gonna replace it with the cathode. It's gonna undergo reduction and it's gonna get plated, so it's getting bigger, it's getting fatter, or like, that's to memorize the sentence. And the other material here, so this is your red fat cat, it's in the cathode position, it's going reduction, and you're getting building up material on it where this is decreasing in size and undergoing oxidation. So that's where you use the phrase. And your anode's gonna be to the positive terminal, and you're gonna dip it in a solution that's preferably of metal. And the metal gets oxidized, and the ions travel to the object being plated, where they get reduced and stick to the object. Here they're showing us when you want to electroplate a spoon with silver. This is at the cathode, this is at the anode, this is undergoing oxidation, this is undergoing reduction. And this is gonna get smaller in size later on. And yeah, an iron spoon is to be plated with copper metal, right? The two half reactions. So at the cathode, you're undergoing reduction. So Cu2 plus 2E. Reduction, always you have your electrons in the reactant side. So Cu2 plus 2E gives you Cu, and at the anode it's gonna be the opposite. Cu gives you Cu2 plus 2 electrons, because it's being oxidized. Here they're asking us which of the following could you use the apparatus to electroplate iron nail with nickel. Since you want to plate it with nickel, your solution should have nickel in it. And we said that your iron, or the thing you want to plate, should be your cathode. Cathodes are at the negative. Cathodes are the negative ones, but they are attracting positive ions towards them. So your iron nail should always be at the negative terminal, where your metal should be at the positive terminal. And yeah, and the solution should always have the thing you want to plate with in it. So here it's wrong because the iron, here it's wrong because these are switching places. Here it's wrong because the iron and they're in the wrong places. Here you can't just have nickel, you have to have a solution, aqueous solution of it. And this paragraph, just read it and read the advantages and disadvantages, because this really can't be explained. It's just telling you about a different thing to replace a different type of renewable energy, and it has advantages and disadvantages like others. And you answer these questions from this table or from this paragraph. You have to read it. And here we start our top questions. These questions sometimes tend to come in the written parts. Now to begin, question 21. It's asking us which of the following electrolytic cells form gases at both of its inert electrodes. So first we have sodium iodide, so NaI, plus water, H2O. And you know what we're gonna do, of course. So Na and H, it's gonna form hydrogen gas, H2 gas, between Na and H. And between I and O, the I is gonna win over the OH. So you're gonna have iodine in your final. These are gonna get displaced from the reaction, so you're gonna have I, but I is a liquid, so not a gas. And they want the one that forms gases at both of its electrodes. Now, so this one is not the answer. Now, copper sulfate, CuSO4. Between Cu and H, you're gonna have Cu. Immediately you can cancel this out because Cu is a metal, a solid يعني. So it's not a gas. So immediately this one's wrong, and O is gonna win and form oxygen gas, but we have one gas, not two. So this one's wrong. So sodium chloride, NaCl. And Na and H, between these two, hydrogen is gonna win, forming hydrogen gas, which is H2 gas. Between OH and Cl, Cl is gonna win, but Cl itself is a green gas, so it's gonna form Cl2, chlorine gas and hydrogen gas. These two are gases, meaning this is the correct answer. But either way, let's go on to see the other options. These two are molten, so they're not aqueous, so they're not reacting with water. So immediately no, and C is our correct answer. Now here they're asking us which of the following represents reduction. Here, Fe went from having oxidation number 0 to having oxidation number +2. 0 plus 2, it's increasing, so it's oxidation. Oh my gosh, this keeps happening. So it's oxidation. Since it's oxidation, this is not reduction. H2O2 to H2O. Here you're losing an oxygen, so it's reducing the number of oxygens, so this immediately is correct. And between these two, you had to calculate their oxidation numbers. This one's always -2, and you get this one when you calculate the way I told you above. In previous examples, you find this to be 3. Here again, you do the same thing. You find out that the 3 became 6. So the oxidation number for chromium got bigger, meaning it got oxidized, not reduced. If these were in opposite positions, then it would be reduction, but it's not. So here, your only reduction change is 2. Now for question 23. So they're asking us which is the direction of the electron flow in this electrochemical cell. So in this electrochemical cell, it's going to go from the positive to the negative, because that's how electrons flow. And the student replaced the iron electrode with a silver electrode. The voltmeter reading changed. Describe the change and why did this occur. So when you replace iron with silver, the voltmeter reading changed. So we know that the reading increased. Why? Because we know that silver, it's more reactive than iron. Silver is less reactive, but it has a higher tendency to, get reduced. So since it's less reactive, the voltmeter's reading is gonna increase. Here it's asking us when the student replaced the zinc electrode with a copper electrode, the voltmeter gave a negative reading. Why is this? It's because that copper is less reactive than iron. So since it's less reactive than iron, when you replaced it with it, it gave you a negative reading. Now, on to the second part. It tells you a student conducted the electrolysis of concentrated aqueous solution of sodium chloride using the following apparatus. And they're asking us which particles allow the flow of electric current from the sodium chloride in the solution. This is obvious, it's ions. Ions are flowing in electric current in solutions. Give 2 reasons for the use of graphite as the electrodes: because they're inert, they don't affect, and they conduct electricity. These are just things you need to memorize. What is the gas produced at the anode? So at the anode, which is the positive terminal here, you had sodium chloride. Chloride is the negative ion that's gonna be turned into chlorine gas when it's electrolyzed, and it's gonna go towards the anode. Because it's negative, it gets attracted to the positive electrode, which is the anode. So it's gonna not go as chloride, it's gonna go as chlorine gas. So here you're gonna have chlorine gas. And the half equation for this reaction at the anode, we know that at the anode it's oxidized. So since chlorine is oxidized, it's gonna become from Cl minus, which is the ion it was in the solution, to chlorine gas and 2 electrons, because this is the half reaction. Now here you have a blue litmus paper is dipped in the remaining solution after the electrolysis is over. Does the blue litmus paper change color? No. Why? Because the things you had left in the solution. So we had sodium chloride, which is NaCl plus H2O. The H2 turned into hydrogen gas and the Cl turned into chlorine gas. So you're left with, not the H2 by the way, it's H and OH, HOH, which is H2O, but we write it as HOH. So have H went and turned into hydrogen gas, OH and Na stayed in the solution, forming NaOH. NaOH is basic. So no, the litmus paper that's blue didn't change into red, because it only changes into red if you have an acid. Here you had an base, so it won't. Now, CQD 24. The question tells us that the electrolysis is used to break down ionic compounds. Student conducts an electrolysis for a concentrated solution of copper chloride. Why is it recommended to use inert electrodes? Like we said, we don't want unwanted reactions happening. And a solid deposit is observed at the negative electrode. So you had CuCl 2 plus H2O, because it's a solution. Between Cu and, this is HOH. So between Cu and H, the Cu will win because it has a higher tendency. So it's going to form a metal, which is the solid deposit they're talking about, which is going to happen on the negative electrode since this is the positive ion. So on the negative electrode, the Cu is going to form. And I think these are switched, but sure. Doesn't really matter for this question. Write the ionic half equation for this reaction occurring at the negative electrode. You're going to have copper ions, so Cu2 plus. At the negative electrode, which is the cathode, you're going to have reduction. So Cu2 plus 2 electrons is going to reduce into Cu. Now, a fizzing observed at the positive electrode, at the anode. Identify the gas released and how does it form. So between Cl2 and OH, we know that Cl2 is gonna form the gas. It's not OH, because it has a higher tendency than OH. Since Cl2 is gonna form the gas, it's chlorine gas, because that's what you have in the equation, and it gets oxidized, and that's how it forms, because it's at the cathode. Now, and then identify the species that it gets reduced to in the solution going electrolysis. What gets reduced at the cathode? The copper will go at the cathode and get reduced. The ions, specifically. Because see, at the cathode, we started off with Cu2 plus, which are ions. Student wants to electroplate an iron rod with chromium. So the electrode that the student should place the chromium rod at is the anode. We don't want it to get reduced. We don't want it to get red fat cat. Remember, the thing that you want to plate should be at the cathode. So the thing we don't want to plate, the iron rod, the thing that's gonna plate it, should be at the anode. The chromium. The chromium should be at the anode to plate the iron. What would the electrolyte be suitable for this electrolysis? You have to take a solution with the thing you're plating with, chromium nitrate, or any solution, doesn't have to be nitrate. Write the ionic half equation occurring at the negative electrode. So you have at the negative electrode, which is the cathode. At the cathode, you have reduction. So the chromium, Cr3 plus, is going to get reduced with 3 electrons and become Cr. And the electrode oxidation happens at the anode, because it's red fat cat, cathode, reduction, oxidation, anode. Why chromium is used in the electroplating? There's always 2 answers for this. To give it a better look, or to make it to better its look, or to protect it from corrosion. These are your only 2 answers for why do you electroplate something. Now we have the top question 25. a student conducts electrolysis on a dilute solution of sodium chloride using the apparatus shown below. Gas X makes a pop sound when it's tested with a lighted splint. There's only one gas that makes a pop sound when tested with lighted splint, and that's hydrogen gas. Suggest a test for oxygen gas and include the result of your test. For oxygen gas, we know that there's one test. When you put a glowing splint near the oxygen gas, it's gonna relight. So when you put a splint in front, not a glowing splint, let's see what they had in their answer here. Approach a glowing splint, yeah, it's a glowing splint, it will relight. Suggest a material to be used as an electrode and give one reason why it is suitable. We said graphite, and it's because it's inert or because it's conductive. Now we have 26. What's the process shown in the figure called? It's called electrolysis. Whenever you see a figure like this, electrolysis. What are the observations you expect to see when you, on the positive electrode, you're breaking down PB, BR? 2, probably. So, because it's PB2 plus BR, you'll take but that's not relevant to what we're taking today. So, what do you expect to see on the positive electrode, which is the anode? You're gonna see the negative thing, so BR, but either way, you're gonna see bubbles. Always when they ask for observations, you're most likely gonna see bubbles. Now, a Bunsen burner is used to melt solid lead bromide. How can the student adjust the flame to give the hottest flame? This is from last year's chemistry. The answer is gonna be open the air hole, because it's gonna let in more air and give you a hotter flame. Why is it recommended to use graphite electrodes? Because they're inert. When replacing molten lead bromide with an aqueous solution of lead bromide, hydrogen gas is produced at the negative electrode and bromide gas is produced at the positive. How do you test for hydrogen gas? We said when you approach it with a splint, a glowing splint, you will hear a pop sound. And that's the observation. Bromine gas, always you can identify it because it's producing brown bubbles. Bromine, brown. Remember it like that. Lead bromide is classified as a hazardous chemical. Suggest a safety precaution when dealing with lead bromide. You don't want to touch it since it's hazardous, and you don't want it bubbling into your eye because we know it's forming bubbles. We don't want the bubble to pop into your eye, so you have to wear gloves and goggles. Either one will give you the mark, but I prefer you write both. Now, last question for today. A student conducted 2 redox titration experiments to investigate the reactions between aqueous solution of potassium manganate and 2 aqueous solutions of iron sulfate. Solution R and solution T are of different concentrations. You have experiment 1, a 50 centimeter cube burette was filled with potassium manganate solution to the 0 centimeter mark. 25 centimeters of solution R were measured using a pipette and poured into a conical flask. Potassium manganate solution was added to the flask while shaking until a pale pink color appears. You have a burette and it shows the following measurement. So they're asking you for the final burette reading. So what you do is you have to look at the white space and see where it ends. So this is 16. First you have to identify how much is between each tiny space. So we do that by counting the spaces and then dividing it by how much difference. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the difference here is 1. So 1 divided 10, making each space 0.1. So this is 16, 16.1, 16.2, 16.3, 16.4, 16.5. It's going to stop at 16.6. So that's your final burette reading. Now, calculate the volume of the potassium manganate solution used in centimeters cubed. I just realized I accidentally paused it without noticing, and I was explaining to nothing. So anyways, the volume of potassium manganate in the solution used was 16.6 centimeters cubed because you had to put enough to cancel out the solution you put. Now in experiment 2, 25 centimeters cubed of a solution T were measured in the experiment, and experiment 1 was repeated. but this time it wasn't refilled to the 0 mark. So now you need to find the final reading in centimeters cubed. So we have the reading here, or well, you have to find out how much potassium manganate was used. So you had an initial reading and a final reading. First we need to read the final reading, which was 38, 38.1, 38.2, 38.3, 38.4, 38.5, 38.6. That you just put it down easy. Now calculate the volume of potassium manganate used. How do you calculate it? You take 38.6, which is your final reading, and you find your initial reading, which is 10.1, 2, 3, 4, 10.4. You subtract the two from each other and you're gonna get, so 38.6 minus 10.4, you're gonna get 28.2. Now, which solution is more concentrated, R or T? T is more concentrated. Why? Because you needed more potassium manganate to change the color. You needed more than the last one to change the color, so it's more concentrated. If in experiment 2 the student used 50 centimeters of the solution T instead of 25, what would the volume of potassium manganate be needed to reach the endpoint? Instead of this number, 28.2, you'd have to double it because you used double the amount of solution T. Now, what issue will the student face if they were to titrate 50 centimeters of solution T? You wouldn't have enough solution in the burette. Because if you used, because the burette is 50 centimeters cubed. If you need 56.4 centimeters cubed of potassium manganate, it won't fit in a 50 centimeter cube burette. So yeah. And another student conducted the same experiments using a measuring cylinder instead of a pipette. How would their results differ? Of course, using a measuring cylinder is going to be way faster than using a pipette, but way less accurate because the pipette will be very, very accurate. Indicators are used in most titration to determine when the endpoint is reached. Why was no indicator used in this titration? Now, why was it not used? Because look, as if we can go back to the question, when you add the potassium manganate and shook it, a pale pink color appears. You didn't have to add a indicator for the color to change. The solution already changes the color by itself. And that's the end of all the CQDs for chapter 4. Hope you understood. Have a good day.